Okay guys, this is chapter 2A, talking a little bit about chemistry, biological systems, just very, very basic biology. A lot of this stuff, if you don't know it like cold, it's not that big of a deal, but it does inform your ability to kind of think through problems. So the more intimate of an understanding you have of biology and chemistry and physics, the better you can reason through some problems later on as you get to the test, right? If you just know how things work, it's a little bit easier. Okay, so let's go ahead and run through it real quick. All right, so you're going to know how matter comprises atoms and molecules that move along different systems. Water is an important component of most environmental systems, whether it's solid, liquid, or gas. What I want you to write down right now is that water is one of the most common greenhouse gases. Very, very important. So water is a greenhouse gas. It's the one that everybody forgets, so I don't want you to forget that. We discuss how matter is conserved in chemical and biological systems. This is going to be very important later when we start talking about combustion reactions inside internal combustion engines and looking at how things like N2O end up forming in the atmosphere, another powerful gas that goes in the atmosphere. It can lead to acid rain and also destruction of some of the ozone layer. All right. Matter is anything that can occupy space and has mass. Mass being different than weight, right? Weight is the force gravitational that acts on mass, okay? So if you're on the moon, you have less force gravitational, so there's less weight on you, less weight pull, but you have the same amount of stuff inside your body. All right, here's an atom, the smallest particle that can contain the chemical properties of an element. Of course, it can be broken down into subatomic particles, but it's not going to have the same properties as the atom itself. An element of the substance composed of atoms that cannot be broken down into smaller, simpler components, and still be recognized as that same element. Okay, the structure of an atom. An atom is composed of protons, neutrons, and electrons. You're going to learn this more in chemistry. You should have already known this from before. Negatively charged electrons surround the nucleus. This right here is called the Bohr model, where you have like this kind of planetary-looking system here. This is not currently what we understand the model of the atom to be. We use more of like an electron cloud of probability, but this is a simple and instructive method of teaching students what the general structure and composition of atoms are, right? So just because a model is not necessarily most representative, it doesn't mean it doesn't have some sort of purpose that can help us make simple calculations or teach. All right, periodic table, chart of all chemical elements currently known, organized by their properties. We add elements to this table every so often by using things like particle accelerators and colliders. They're very unstable elements, so they don't last for very long. But we do that every couple of years, and the country that does it gets to name it. It's really fun stuff. All right, molecule. Particle contains more than one atom. Okay. Compound contains more than one molecule. Right? Okay, the atomic number is the number of protons in a nucleus. Make sure you know that. I don't think it'll be tested too much. When we start getting into nuclear decay, we start talking about pollution and fallout. This sort of thing is going to come up again, so you need to know it in the context of that. Mass number, the total number of protons and neutrons. Remember that the neutrons have a slightly higher mass than protons, and that matters when you start talking about mass defect later on. The isotopes have the same element with a different number of neutrons, so it has a different mass. Okay. A radioactive decay, the spontaneous release of material from the nucleus of a radioactive isotope, and that can be beta particles or alpha particles, right? Antineutrinos, all that stuff. Gamma rays, gamma particles. Okay, half-life, the time it takes for one half of the original radioactive parent atom to decay. So later on we'll talk about this a whole lot and we'll actually do calculations. If you've done chemistry before, it is not going to be a really complicated equation. I have a very simple way of showing how that works. Okay, a covalent bond is shared electrons. All you need to know about covalent bonds is that they are shared electron pairs. Okay, they're not being ripped away. It's not like an ionic bond like sodium chloride. Right, where this is like a +1, that's a -1, and so the chlorine will lose its electron to this guy. It doesn't work like that. There are three types of chemical bonds: covalent, ionic, and hydrogen bonds. The ones that we care about the most right now are going to be hydrogen bonds because that has to do a lot with water. Okay, here we go. So here's CH4, methane. held together by covalent bonds. See that these atoms are shared, right? So these will, in the Bohr model, which we said wasn't necessarily the most accurate representation of how electrons orbit the nucleus, but it's instructive for this particular purpose, right? The hydrogen atom will have 1. This carbon has 4, and you see that these kind of will occupy the same little space right here and be shared in between, right? So that's kind of nice. All right, here we go, an ionic bond. This is what I was talking about earlier, and actually it's the opposite way. Sorry, my bad. The plus means it gives the electron that way, right? Okay, hydrogen bond, a weak chemical bond. It is weak, but it has very, very important applications because of the way that it works. Okay. Hydrogen atoms are covalently bonded. It means they share. So one atom are attracted to another atom on another molecule. So a lot of the times this can cause this to become a polar molecule. One side is more positive and the other side is more negative, kind of like a magnet. So you need to know that polar molecules are like magnets, right? You can kind of think of them as magnets or like something that has a separated charge on the body. So something that if you touch the surface of the car, it can be more negative on one side than the other and you can get shocked. So this magnetic effect can do some interesting things when we're talking about the structure of biological bodies, like lipids and things like that, polar, non-polar stuff. We talked about that. Okay, water is polar because the shared electron spends more time near the oxygen. So if the electrons are negative value, guess what? It's going to be more negative towards the oxygen, right? So it's going to have a more negative charge on one side, leaving it more positive on the other. Okay, so that's going to end up creating things like this, where the negative side reaches the positive side of another. You see, notice how the white end is attracted to the red end? Okay, so this is what ends up happening. And when you end up having a lot of these water molecules link up, you end up with things like surface tension. You end up with things like when it turns into solid state, crystallization, and this will turn into air pockets right here. And you end up with kind of a weird little circumstance where ice will end up insulating air. It'll actually work as a warming component. It can almost work like a blanket, like an igloo. So that's pretty interesting. And also because it holds air in there, it's going to be less dense than liquid water. Water has many significant properties. Okay, surface tension, it all sticks together, right? This is called cohesion, right? This is cohesive forces. Cohesive, like with and hesion together, and so it's holding together the surface. So if you actually place a paper clip, like a really light paper clip, or maybe you've seen a bug, like a water strider, sit on top of water, it is taking advantage of water's surface tension, right? The cohesive forces. The capillary action works on the adhesive forces, which is outside of the actual element. So if you ever notice when you look at, they tell you in biology, you have that, you look at the beaker, you have this meniscus, you want to look on the bottom of the meniscus because right here, this is not the true level of the water. What's happening there is you have, you end up having capillary action, the adhesion of the water sticking to the glass. Okay? At Earth's surface, water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. Now, if you go up in the atmosphere or down in the atmosphere, now there's more pressure, and that changes things a lot. Okay? Many substances dissolve in water because it's polar. It's polar, and it can break things down. It has a polar side, it has a positive side and a negative side. So it's able to kind of attract different elements out of whatever compound comes in contact with water, right? It's a universal solvent. You need to know that. Water is a universal solvent. A lot of life processes on Earth are only possible because water is our liquid. Water is our main liquid. Okay? So that's why we look for water and we search for extraterrestrial life, right? We're not literally looking for ET and aliens and stuff like that, but we are looking for things that we need, right? We assume that life is convergent. You know, when we search for life outside of Earth, we look for convergence theory. So the idea that life on Earth is kind of the norm, like what you need, right? So we look for things that are kind of like us. An acid is a substance that contributes hydrogen ions. Hydrogen ions. You need to know that, especially if you are a chemistry guy right now. Hydrogen ions, acid. So usually you're going to see things like HCl, right? Hydrochloric acid, right? Lowercase, it's lowercase right here, HCl. Or H2SO4, right? Hydrosulfuric acid. So you need to know that if you see a hydrogen in front of something, this is an example of an acid. Okay? The base is a substance that contributes hydroxide ions to a solution. So hydroxide is OH. OH negative, by the way, the hydrogen is going to be positive. Okay? So if you see things like calcium hydroxide, this is a base, right? This is a base, sodium hydroxide. Right? So if you see things like this, this is an example of what a base would look like. Okay? So you need to be able to recognize that. You need to know this in the context of acid rain later on. Okay? Acid rain. And this stuff being introduced into the soil through, and it's very interesting how this stuff gets into the environment through human interactions. You would think it's just like we go to a factory and spill acid into the water, but no, the combustion of coal, the combustion of fossil fuels can release acids like H2SO4 and things like nitrous oxide. It's not necessarily an acid, but just like our human interactions with fire and heat end up creating these substances that get into the atmosphere. They mix with the water in the air. And guess what? Since water is a solvent, it dissolves it very easily, brings it down, and guess what? Now we have acid rain. Okay, pH, the number indicates the relative strengths of acids in a substance. And what you need to know about pH, it goes on a scale where 7 is neutral. 7 is neutral. The higher up you go, it gets more basic. So it's one of the basic guys over here. So you start getting basic this way. And then the lower you go, you start getting more acidic. So just remember, I don't want you to be one of those people who misses this. A lot of people think the higher number you go, the more acidic it is, but it's actually the opposite. And what you need to know really is that hydrogen is a relatively high activity ion, which means it is really likely to switch. It is really likely to switch with elements that are lower activity on the periodic table. And as you go through chemistry, you'll look at that. And so things that are acidic, they react a lot. It's not that acids don't burn because that's what acids do. They burn because that's what happens to the cells in your body when elements switch with hydrogen ions, right? When you touch acid. The same thing's true about bases. Okay? So it's a lot more complicated than just it burns. There's a physics process going on in your skin. All right, so here's that chart again. Really interesting stuff. Look at that. You put that in your stomach, right, when you drink. But look at that. Your stomach is a stronger acid. So if you want to neutralize something a little bit easier than just putting something like sodium hydroxide in your stomach, you want to put something that's a weaker acid. So that way you don't have a really, really big overreaction, right? You don't have an out-of-control chain reaction or anything like that. You want to weaken something with a weaker base before you start doing this. I have a really funny story about putting calcium carbonate into 12 molar HCl, and that was I almost died. That was awesome. The chemical reaction occurs when atoms separate from the molecules or recombine with other molecules. But you need to know here that mass is conserved. Okay, you are not, when you do a chemical reaction, you are not losing any of these atoms. If you added up all the atoms on one side and added up all the atoms on the other side, you would have the exact same number of each atom on both sides, right? Now you might have to do some balancing and a little bit of proportions, but you end up with the exact same number of everything on each side. All right, inorganic compounds. Generally speaking, when you look at inorganic compounds, you're looking at stuff that comes from these two portions of the table. So when you combine stuff from over here, these are usually going to be inorganic. The organics are going to be from here. You're going to combine these guys right here. So maybe 2 from this section, inorganic from these 2 sections, okay? All right, carbohydrates, proteins, nucleic acids, these are all the stuff of life, okay? These are macromolecules, which means that they are made of, at some point, probably carbon. Carbons are really nice because they have 4 electrons surrounding them. And so because there's 4 electrons and you need a pair of electrons to make a bond, it really just needs 1 more electron on each side to make a chemical bond. So the really nice thing about that is that it has a lot of real estate to be able to hold on to different atoms and ions. So you end up making almost like... What? You almost end up making like a Jenga block sort of thing, right? Where you can... so maybe you stack cross-section this way. Or, I mean, I'll just show you. So you got 1, 2, 3, 4, then you get a carbon. Then look, it's got 1, 2, 3, and look, 4. And then look, you put another carbon, 1, 2, 3, 4, and then look, you got another carbon, 1, 2, 3, 4. So you see, good morning. Sorry, I'm like sitting in the cafeteria right now. So you see that all these bonds are here are what were necessary to make that, those 2 electrons were necessary to make that bond. And carbon lends itself really nicely to chaining up, right? So you get these macromolecules. And if you ever get to look at DNA, and like see it all raveled up and everything, it's really cool. It just looks like a gigantic ribbon of mess. All right, and then of course the cell. You should know this. Go ahead and look at that. All right, guys. Bye.